Hi everyone, and welcome back. We're going to continue our discussion of electric fields due to continuous charge distributions today. Last time we calculated the electric field of the center of a circular arc of charge and a straight uniformly charged wire. Now we're going to do two more. We're going to find the electric field due to on the axis of a thin ring of charge and the electric field due to a uniformly charged disk. So, starting with the electric field on the axis here at point P of a thin ring of charge, find the electric field at a point on the axis. If the ring has a radius r, it's uniformly charged as shown in the diagram. And once again, really all of the work, the physics, is in the setup of the problem. So, our general strategy here. We can make another symmetry argument because the hoop is circled around the axis and P is on that axis, that really the only electric field we're going to have to deal with is here in the z direction. Everything else is going to cancel out because it's uniformly charged. That'll simplify life for us a little bit. So let's see, we'll follow the same strategy again. I'm going to break up my thin ring of charge into little infinitesimally small pieces with some charge, delta Q, in each one. And as I look at that, what I'm going to do is I'm going to draw a straight line from that charge to my point P. We'll call that Ri, the distance to my little I piece of charge over here. This angle will be theta I. We'll have some electric field here, E, due to that little bit of charge I. And notice now we have a theta I, but we've got another angle we have to deal with, an angle around the circle. I'm going to define then my angle phi as the angle around the circle in that direction. So there's phi. Now again, we have a linear charge density. So let's say that lambda, again, is the total charge divided by the total length, which in this case is going to be q over the circumference, or 2 pi capital R. Delta Q, on the other hand, is going to be our linear charge density lambda times the length of that little section, which is going to be r, our radius, d phi. I think we're just about there, but let's take a look at a couple more items. Ri, just like we did in our last problem, we're going to take a look and see that, we make a right triangle here again for Ri, where Ri is going to be equal to the square root of z squared plus r squared. And we've got this theta I, but let's state here that the cosine of theta I, cosine adjacent over hypotenuse, our adjacent is going to be our z value, so that's going to be z over our hypotenuse Ri, which is z over, we just said Ri is square root of z squared plus r squared. And with that set up, we should be able to start looking at calculating the electric field in the z direction due to this thin ring of charge. All right. To begin with, the electric field, due to some little bit of charge, I, in the z direction, is going to be EI times the cosine of theta I, which of course is going to be 1 over 4 pi epsilon 0 delta Q over Ri squared, our distance from the charge to the point at which we want to know the field, times the cosine of theta I. And here begins the fun. This is going to imply then, right away we know that Ri is z squared plus r squared, and cosine theta I is z over square root of z squared plus r squared. So I'm going to rewrite this as EI in the z direction is equal to 1 over 4 pi epsilon naught. We've still got our delta Q over z squared plus r squared times cos theta I, which is z over z squared plus r squared square root, or raised to the 1/2 power. Well, z squared plus r squared times z squared plus r squared to the 1/2 is going to be z squared plus r squared to the 3/2. So we can rewrite this again as ei in the z direction is 1 over 4 pi epsilon naught. We have z over z squared plus r squared raised to the 3/2. And we still have our delta q here. But remember, delta q is lambda r d phi. So, lambda r d phi. Now my next step here is I'm going to integrate both sides. If I take the integral of the left-hand side, the integral of e due to that little bit of I in the z direction is just going to be e in the z direction. The integral of the right-hand side is going to take a little bit more work. But as I look at this, I have a bunch of constants here. Z is a constant, 4 pi epsilon naught is a constant, z and r are both constants, so all of this is a constant. Lambda is a constant, r is a constant. My only real variable here is my d phi. So when I go to rewrite this, I'm going to come all the way down here to write it. E in the z direction is going to be equal to, I've got 1 over 4 pi epsilon naught times that constant z over z squared plus r squared to the 3/2, and I've also got a lambda r. Well, where am I going to put that lambda r? I'm just going to put it right over there for now. There's my lambda r times the integral of d phi. And my limits of integration? Well, I've got to go all the way around the circle. So that's going to be from phi equals 0 to 2 pi. And the integral from 0 to 2 pi of d phi is just going to be 2 pi. Therefore, e in the z direction, when I go through here, is just going to be 1 over 4 pi epsilon naught. I'm going to have a 2 pi times z over z squared plus r squared to the 3/2. And of course, I still have my lambda r. 2 pi and 4 pi, well, that's just going to be 2 in the denominator, lambda r over 2 epsilon naught, z over z squared plus r squared. But we also know that lambda, if you recall, we defined as q over 2 pi r. So putting that all together, the z component of the electric field is just going to be 1 over 4 pi epsilon naught times zq divided by z squared plus r squared raised to the 3/2. And if you look, the actual integration here was actually really simple. Our actual integration is the integral from 0 to 2 pi of d phi. Everything else comes out as a constant. The real work is in the setup of the problem. So, the electric field on the axis of a thin ring of charge. Let's go on and do one more. The electric field due to a uniformly charged disk. And you'll notice this is very similar to the previous problem because we already know what the electric field is due to that ring of charge. So our strategy here is going to be to make a bunch of different rings, starting with small rings and making them bigger and bigger and bigger, and add up the electric field due to each of those rings as we go from a radius of 0 all the way to the radius of the disk, capital R. Again, we can make the same symmetry argument that the only electric field is going to be in the z direction. So we'll define this delta R for one ring as we go from R equals 0 to capital R. Delta Q contained in that ring, charge of that ring is delta Q, And now we're going to use an area charge density. We're going to say that sigma, our area charge density, is going to be the total charge divided by the area of the disk, which is Q over pi capital R squared. Delta Q, by that token, the charge contained in that ring, is going to be our surface charge density times the area of that ring. And how do we get the area of that ring? Well, if you think about it, take that ring in a circle. What would happen if you cut it and spread it out? Well, the circumference of that is 2 pi r, so that'll be 2 pi Ri for our little bit of radius for that ring, times delta R, the thickness. So there's how we can get our delta Q. And with that, I think we're ready to begin this problem. Let's start off again by finding the electric field due to that little piece, EI, and again in the z direction, 1 over 4 pi epsilon 0 times z delta Q sub I over z squared plus Ri squared to the 3 halves. How do we know that? We just did it in the last problem. That was our answer. Now, our next step here is recognizing that delta Q is just going to be sigma 2 pi Ri delta R, or in this case, dr as we set up our integration, so that E in the z direction, if I integrate both sides, is going to be, and I'll already pull out the 1 over 4 pi epsilon naught, that's going to be the integral of z sigma. Well, let me actually rewrite that on the next line down. Ez is going to be 1 over 4 pi epsilon naught integral, and our integral is going to be our z, times our delta Q, sigma 2 pi Ri dr divided by z squared plus Ri squared to the 3 halves. Now, as we look at this, we've got a 2 pi and a 4 pi here. Well, we've got some cancellations there. The pi's cancel out. The 2, that becomes a 2 over there, so 2 epsilon naught. Sigma and z are both constants, so let's pull those out. Make that a sigma z over there. We've still got Ri dr over z squared plus r squared to the 3 halves. So this integral then is going to be Ez equals sigma z over 2 epsilon 0 integral from r equals 0 to capital R, the entire radius of our disk, of, well, what do we have left? R dr over z squared plus Ri squared to the 3 halves. Now, to do this next part, we're going to do an integration by parts. We're going to take a look and we're going to say, we're going to set this z squared plus Ri squared, and we're going to call that u. So we're going to say that u is equal to z squared plus r squared. If that's the case, then du would be 2r dr. So if I set it up so that it fits that form to have du over u, I need a 2 here. I'd better put a 2 over there as well. Now I've got this constant times the integral of du over u. Pardon me, du over u to the 3 halves. Well, that's just u to the negative 3 halves du. Or when I integrate that, what I'm going to find is that Ez then equals sigma z over 4 epsilon 0, the integral of u to the negative 3 halves du. Well, that's just going to give me negative 2 over u to the 1 half evaluated from r equals 0 to capital R. Okay, well, from 0 to capital R, we changed our variables. We went, instead of from 0 to capital R, we changed our variable to u and du. So instead of u and du here, we need to go in terms of our variables. So that will be from 0 for r becomes z squared, and z squared plus r squared as our limit up here, changing our variables. This implies then that the electric field in the z direction must be sigma z over 4 epsilon naught. Now I'm just going to plug in my limits of integration here, times -2 over the square root of z squared plus r squared minus -2 over, well, square root of z squared is just going to be z. Or, simplifying that, that's sigma z. You can pull a 2 out of both of those. So 2, oops, let me clean that up a little bit. Sigma z over 2 epsilon naught times 1 over z minus 1 over the square root of z squared plus r squared. And I can factor a z out of this if I want to. Multiply z here, multiply by z there. And what I should end up with, and give us a little bit more room here. Just a little bit of algebra now. The electric field in the z direction at that point P should be sigma over 2 epsilon naught times the quantity. If I multiply by z here, put the z back in, I get 1 minus z over z squared plus r squared square root. All right, let's take this just one last step further. Instead of just looking at the electric field due to a disk, what would happen if you expanded that disk? That radius kept getting bigger and bigger, infinitely bigger. You'd eventually have a plane, right? So we can figure out, based on our answer here, what the electric field is due to an infinite plane. All we have to do is take the limit as capital R approaches infinity of our answer. So sigma over 2 epsilon naught times the quantity 1 minus z over square root of z squared plus r squared. When we do that, as capital R approaches infinity, this term's going to get really, really big. The square root of that's going to get really, really big. And really, we're going to see this term become 0. So what we'll end up with is sigma over 2 epsilon naught times 1, or just sigma over 2 epsilon naught. The electric field due to an infinite plane is just sigma over 2 times the permittivity. Doesn't matter how far away you are from it. No dependence on distance. All right. Hope that gets you a little bit further with continuous charge distributions and electric fields. I know they take a little bit of time, some practice, so highly recommend you get some more practice doing these on your own, doing some other charge distributions until they become comfortable. Thanks for your time and patience. If you need more help, check out aplusphysics.com. Make it a great day.